So what if the geometric rules that we've been using for literally thousands of years are actually holding us back? Today, we're going to dig into a really revolutionary idea, and it all starts with the simple shapes you might find in your garden, but it ends with us questioning the very fabric of the universe itself.
This question, from the legendary physicist Richard Feynman, it really gets to the heart of a deep, deep mystery. We see symmetry everywhere we look, but it's rarely perfect, right? It's almost perfect. And for centuries, that little word almost has been this huge scientific puzzle.
I mean, just look at this. On one hand, you've got the world of pure math, perfect pentagons, flawless circles. But then, on the other hand, there's the real world. A starfish clearly has 5 sides, 5-fold symmetry, but no two are exactly alike. They aren't the rigid, perfect shapes from our textbooks. So here's the question. Is nature just a little bit messy and imperfect, or are the tools we're using to describe it totally incomplete?
And that leads us to the core idea we're exploring today. What if the imperfection isn't in nature at all? What if it's in our perspective? For literally centuries, we've been trying to cram the beautiful, fluid, organic shapes of the living world into this very old, very inflexible box.
Just think about it for a second. From the moment we learn about shapes in school, we're taught about these ideal forms. Perfect straight lines, perfect circles, exact squares. Our whole scientific language, our way of seeing the world, it's all built on this foundation of geometric perfection, of rigidity.
This way of thinking, it has such a long history. It's so fundamental to how we see things, we barely even notice it's there. But it was built piece by piece, tool by tool, axiom by axiom, over thousands of years.
It really started way back with the ancient Egyptians. Their rope measurers used these ropes with fixed knots to draw property lines after the Nile flooded. Then it was supercharged by Descartes, who gave us the XY coordinate grid that we all learned in school. And it was finally cemented in the 19th century with this basic assumption that a 1-meter ruler is still 1 meter long no matter where you take it. These were the tools that built a rigid world.
Now, this toolkit, it's been unbelievably powerful. It gave us physics, engineering, all of modern technology. But what about all the things that just don't quite fit? The starfish, the flower, a living cell. What if trying to describe them with rigid rulers and perfect circles is kind of like trying to describe a flowing river using a set of bricks? It just doesn't work.
Okay, so if the old tools are the problem, what's the solution? Well, this is where a truly groundbreaking idea called the superformula comes into play. It suggests that there's a single master key, a kind of hidden code that can unlock the true geometry of the natural world.
Now, don't worry about the complex math for a minute. Just get the concept. This is a single, beautiful, unifying formula that basically acts like a recipe for nature's shapes. And by just tweaking a few numbers in that recipe, you can generate this incredible diversity of forms we see all around us. And the power of this formula is just how well it maps to reality. It can generate the simple, familiar shape of a clover.
Or you just tweak a parameter, and now it's describing a totally different flower, a more delicate one with a different number of petals.
Or you can even generate the more complex 5-fold symmetry of a starfish.
And here's the key. All of them, as different as they look, are just variations on a single geometric theme. This isn't a bunch of different formulas for different shapes. It's one idea expressing itself in all these different ways.
So here's a really great way to think about it. For thousands of years, we've been drawing shapes with a rigid string, which gives us perfect circles. The superformula is like throwing away that string and using a perfectly elastic band instead. It allows the radius, the distance from the center, to stretch and shrink in just the right way to create all of these other amazing shapes.
But this simple idea of a flexible ruler, well, it actually requires a whole new way of thinking about geometry itself. It means we have to trade in that old rigidity for something brand new, something called ultra-flexibility.
Okay, so in the geometry we all know, a point has no dimensions. It's just a location. But in this new way of looking at things, a point is more like a tiny nugget of gold. By itself, it has no size, but it holds all the potential to be stretched out into a line or a plane or any other shape, all without losing its fundamental identity.
And this image right here, this illustrates the huge mental shift. From our outside, God's eye perspective, it looks like the radius of that circle is stretching out to form the corner of a square. But, and this is the crazy part, for an observer inside that geometry, living on that line, the distance to the edge always feels the same. It's not that the distance changes, it's that the ruler itself stretches right along with the shape.
So, what we're talking about here is a really fundamental shift in thinking. We're moving away from a world of rigid, fixed, and unchanging Euclidean rules to one that is flexible, stretchable, and adaptive. Just like the natural world it's trying to describe.
Okay, look, a new geometry for starfish is pretty cool, but the implications of this idea go way, way beyond biology. If the very foundation of geometry itself is flexible, well, that sends shockwaves through basically all of science.
And I'm not kidding, these shockwaves are massive. This new framework doesn't just describe flowers, it actually generalizes the Pythagorean theorem, one of the cornerstones of all mathematics. It seems to resolve ancient logical puzzles like Zeno's paradox. It even gives us a totally new lens to look at some of the biggest questions in physics, like what really happens to information inside a black hole.
Think about a black hole's singularity, for instance. In classic physics, when something collapses down to a single point, all information about it is just destroyed. But in this new geometry, a point actually keeps the shape DNA of whatever it came from. The information isn't lost, it's just encoded in a point of zero size, ready to re-emerge.
And sometimes the parallels are just stunning. On the left, you see the growth pattern of bamboo with its nodes and hollow segments. It's a natural cycle of growth and reset. Now look at the right. That's a diagram from physicist Roger Penrose's theory of a cyclical universe. The incredible thing is that, geometrically, they're telling the exact same story. A story of information passing through a crossover point and then re-emerging, whether that's in a plant or at the very end of the universe.
So we come all the way back to Feynman's big question. Why is nature nearly symmetrical? Well, the answer this new geometry gives us is both powerful and incredibly simple. Nature is perfectly symmetrical. It was our rigid, circle-obsessed rulers that were the problem all along. The near symmetry was just an illusion, created because we were using the wrong tools for the job.
And that leaves us with a final, absolutely fascinating thought to chew on. For more than 2,000 years, we've built our entire understanding of reality on a geometry that might only be one special case. So if we were missing something this fundamental, this basic, what other simple, elegant truths about our universe are just hiding in plain sight, waiting for us to find a new, more flexible way to look?